Lab 2 by Cameron Akbarzadeh. In this lab, I dropped a stress ball shaped like a piece of potato bread from 1.397 meters to the ground. The mass of this bread-shaped ball was 0.024 kilograms. The aim of this lab was to create a computational model for a falling object that has a non-zero net force and starts a rest. We found out that the model almost approximated the motion of the falling object when drag and gravity are taken into account. The experimentation took approximately 0.5 seconds. We found the weight force on the system by multiplying the mass of the ball by the gravity, which is 9.8 meters per second squared, by the unit vector for the y-axis, which is 0, 1, 0. For the first position versus time graph, I compare the observations to the model that only takes gravity into consideration by using Newton's second law of the final velocity equaling the initial velocity plus the net force over the ball's mass multiplied by the change in time. This formula derives the position equation of the final position equaling the initial position plus the average velocity multiplied by the change in time. As you can see, the observed model is not as close to each other as they could be, and since drag isn't taken into account, it's not as accurate. For the next model, I had to take drag into account, so the proportionality constant, or B, for the magnitude of drag force had to be found. This was done by looking at different vectors on the Python shell and seeing when the y vector would be approximately the last y of the observed model. Thus, a value of negative 0.03886 was found. Then I had to put drag into the equation. So I made the net force equal the weight force plus the drag force and took that into the account of the Newton's second law equation. The model with gravity and drag was closer to the observed model but not as accurate as it could have been, which could be due to camera angles skewing the point mass on tracker or because of a really small drag proportionality constant. Regardless, the model with drag and gravity predicts terminal velocity reasonably well, because terminal velocity is when the force of gravity equals the drag force. This only happens when there's a drag force, meaning that the model with drag predicts a terminal velocity. If the object happened to keep falling, it would reach a terminal velocity at some point. Also, if the object was initially thrown downward, the terminal velocity would still be the same, but it would just reach the terminal velocity much quicker. Thus, the model that takes gravity and drag into account is a more accurate model to predict downward motion.